Hello everyone, my name is Oliveira. I am a PhD student supervised by Professor Gemar Rifel. And today I'm going to talk about IFSCube, an astrophysics tool to analyze data cubes of integral field spectroscopy. So first of all, what is integral field spectroscopy? So integral field spectroscopy is a combination of spectrograph and imaging capabilities or techniques using optical or infrared light to get spatially resolved spectra of a bidimensional field of view in the sky. It's a big definition. So actually is a smart way to take the optical spectrum in two-dimensional space, in two dimensionals. So we call the combined spectra data cube with two spatial dimensions and one spectral dimension associated with the spectrum of each pixel in the galaxy. So here I bring three examples of how we can do that. The first one, the lenslet, we have a microlens array where the light, the observed light is split in the spectrograph inputs, and we have the diffracted light to compose the data cube. The second one, the lenslet plus fibers. We have a bunch of fibers organized, and they are plugged in the focal plane of the telescope to observe the galaxy. And we have também the slicer. Here is the image slicer. Is a series of mirrors that are tilted, so the each image that comes from the sky are different direction to an input of the spectrograph. So we have the spectra of each slice of the galaxy. Okay. So the second thing, how is the gas in galaxies? So when gas is excited by both active galactic eye or stars in a galaxy, it produces emission lines on the electromagnetic spectrum. We can see here these peaks are the emission lines, and we derive the gas kinematic properties or features from the emission line profile that is present in the spectrum. So if the emission line is broad, if it is narrow, if it is different from a Gaussian shape, we can derive different kinematic properties for this specific gas that are emitting this line emission. So next, how we see movement from the spectrum. So we have two major quantities that we derived from the spectrum. The first one is the velocity. So we quantify it by seeing how the center peak of the emission line is shifted from the rest observer. So if the object is approaching us, the frequency observed is increased, and when the object is going farther away from us, the frequency decreased. For wavelength, this thing occurs in the same way, just in the opposite direction. So when the wavelength decreases, the object is going far away from us. So this is the first property. The second one is the velocity dispersion, and we measure that by seeing how broad the base of the line emission is. If the line emission is very narrow, the gas is not very perturbed or shuffle, I don't know the right word. and if the base of the emission line is very broad, we have a gas that are very disturbed from the point of view of the galaxy. So here we have a visual representation of the gas in different velocities when we observe a galaxy. So as you can see in the bottom spectra, when we pass the slice in the data cube for different wavelengths, we can see in the left the gas that are approaching us, and in the right the gas that are going away from us. That's why we see this movement to the right. Here we are seeing the gas that are approaching. Here we are seeing the gas that are going away from us. So, what is IFSCube and what does it do? So IFSCube is a Python package designed to perform an analysis test in data cubes of integral field spectroscopy. The package is mostly used for modeling the emission line profiles using multi-Gaussian or multi-component that we call function or Gauss-Hermite function. This is the functions, this dotted black line, functions that are fitted to the real line emission. After the modeling, we can get kinematic features, as I said, of the gas, like velocity and velocity dispersion. By separating each emission line in different components, we can isolate and study different behaviors of the gas in the galaxy. So, as I said, when we get a broader emission line, we are seeing a gas that are more disturbed. When we see a narrow emission line, we are seeing the gas that are more organized. So the authors are Daniel Crucial-Dutta and Bruno Dallagnol de Oliveira. Here I am showing how the Gauss-Hermite emission line profile works. So when we have two major parameters that change the shape of the emission line, that are H3 and H4. When we have H3 different from 0, can be positive or negative, we get wings shape in the line emission. So we can see the distortion in the line emission, and when we have H4, we have like this step up shape here that elevate the base of the emission line. So here are what we get after using the IFSCube. Here are maps of H3 and maps of H4. We use the Gauss-Hermite fitting for actually as a proxy. So when this map is not all color with the same all color, it means that there are emission line profiles that are different from Gaussian ones. So we spotted that, and after we can see that we have this different profiles. We then decide how many components Gaussian components we will use to analyze our galaxy. So the first one, so we can, as example here, constrain the first component to follow the movement of the galaxy. So here it presents the same pattern of the stars. And the second component we can constrain to the gas that are more perturbed or not gravitationally bound with the galaxy. So we have here all galaxy in this map, that all velocities, these are velocity maps. All maps, all values here are negative, so all this second component gas are approaching us and are not associated with the movement of the galaxy. So to finish, this is the graphical interface of IFSCube. Here we have the map that we can select. The spectra from a specific pixel in the image that we are choosing. Here, this part, we can choose the physical property that we are interested in. And here, here we have this square. Here we have the emission line that we are analyzing. So, for example, O3 or O3 or N2, N for nitrogen or O for oxygen. In the brightest square here, we have the parameters associated with the fit. And that's it.